I came to useR once 2 years ago, and I managed to break my laptop, my computer, like a week or two before that, and it was held together by tape. And this year I did even better. I broke it 2 weeks ago, I fixed it a week ago, and then I lost it on the way here. So I'm very grateful to Rasmus both for lending me the laptop for the presentation. Yeah, here, yeah. Yeah. According to the Tom theory of data analysis, data are abstract numbers with no fundamental representation in the world, and data analysis is the process by which we move these numbers into our brain. But we can't perceive the numbers directly because they don't exist. We have to represent them as worldly forms, such as pie charts or data tables traditionally. And then we look at these with our eyes, and that's how we understand the data. But perhaps we could use something else. Perhaps we could make kebabs, and then we would taste the kebabs, and that could be how we understand the data. And maybe that sounds a bit strange, but the idea is we don't have to stick with these conventional visualizations. Perhaps we could at least go on to music. And so here's an example of a data music. Each different pitch corresponds to a question on this questionnaire. Can you hear it? Okay. And the rhythm corresponds to the results. It's a Likert scale with 6 points, and the rhythm is related to that. And I could show you a bunch more, but I just wanted to give a quick example. And so the talk is about a data music shiny widget, but I need to start to tell you why I thought it was necessary to make such a shiny widget. And so first I'll start with the current state of data music in R. And in order to really understand that, we need to start with the basics of digital audio. Sound is a series of air pressures. The air pressure over here changes, and it hits the eardrum, and that's what we recognize as sound. I will hold this in my hand so that no, maybe this works. Yeah, that's what we recognize as sound. So we need to change the air pressure, and we can do this with a speaker. We move the speaker back and forth like this, and that changes the air pressure. So we need to tell the speaker how to move back and forth, and because it's digital audio, we might say, if the speaker's all the way on the inside, we're going to call that -1, and if it's all the way on the outside, that's +1, and in the middle is 0. And then if we do this, we can send a series of numbers as voltages through the wire to the speaker. So we might say in this example, at time 0, the speaker will be at point 0, which is in the middle. At time 2, it's all the way on the outside. At time 5, it goes all the way back to the inside, that's -1, and so on. This is a curve. I drew it with the curve function, but it's best to think of this, well, the way I do data music usually, I think of it as a vector, a numeric vector inside of R. This is a sine wave represented as a numeric vector. The minimum value is -1, the maximum value is +1, and if we play this through the speaker, we're sending each element of the vector one at a time through the wire into the speaker. If you want to make it sound like music, you have to do a lot more on top of it, like music theory. But in the end, it gets down to this numeric vector. And this is the first of 3 strategies I'll show you for making music in R. So make the numeric vector, then we save that numeric vector as a file, and we play that with some other program. Traditionally, people have used tuneR package, and you do it like this. You have the, maybe I do want to point. Oh well. You have the, you make this this wave. This is the vector we had before. We make it a wave object, and then we use the write wave function to write it as a wave file. And then play is a command from the package sox for playing wave files. I recently have found that I prefer 64-bit little endian floating point PCM files. Because you don't need a separate package for it. This is the whole code. And it's the same idea, though. I write a wave file, and then I play it with play. But either way, that's the file-based strategy. You represent the sound as a vector, and then you save it as a file, and then you play with a command line program. Another approach that was a bit more popular before was to send high-level commands to a specialized audio programming language. Here is one called play it by R. Yeah, this sound was generated by play it by R. I don't actually know what it means. There's also audiolyzer, and this is how that looks. Yeah. What? Bring. Okay. That's as high as I can make it, I think. Yeah. Now, the problem with both of these approaches, with Audiolyzer and Play It By Ear, Play It By Ear doesn't work anymore. Wait. Play It By Ear sends the sound in the end to C sound, which is a separate, I don't really know how it works, separate language or something for making the sound. And it's very powerful, but it has this difficulty of configuring it. Audiolyzer is the same idea. It uses MEX, MSP, and I don't really know, maybe there's something written on top of that. But the idea is it's a separate process, and then you send these commands to that separate process. And this can be very powerful for live performances, for example, because it's a dedicated audio programming language, but it means you have to configure it special for your use, and it makes it so that probably the only people using these two are the people who developed them in the first place. So that's problematic. So another approach that is important to note, I think, but I don't think anyone actually uses, we can interface directly with the operating system sound servers. For example, OpenBSD has SNDIO, GNU Linux, or Linux really, has OSS and ALSA, Pulse Audio and Jackwork from other systems. But this doesn't, well, I technically made one just so I could say I made it, but it isn't actually useful. And the reason is because R doesn't have concurrency, and this is problematic for sound. It means that if you want to play a sound in R, you have to stop everything else you're doing in R. You can only play the sound. So to summarize, we have a few different approaches at the moment for making music in R, and they all leave something, they're all lacking something. We can save the sounds as files, but this is slow because you have to write the file, and then you have to use the external sound player, which will be different for different systems. You can use the specialized sound languages, but that's also annoying to configure, and we don't really have integrations with the operating system level. And so generally it's kind of hard, so I was thinking, how can we make it a little bit easier? I've been talking about the data music for a while, and I show people how to make it with files, but usually people don't do it that way for some reason. So I thought maybe we can make a more accessible approach. I looked at some other tools. This one is Tones and Tune. It's for Excel. It's a very limited, compared to this approach where you have a vector that's your sound, it's very limited in what it can do. Each sound has to be represented as a frequency, and I think it's a fixed time. I haven't used it. Sheet music, it's even simpler than that. It has to be a note, a MIDI note, not even a frequency. And then this is an R package, Sonify, which you think it might be more powerful because it's R, but in order to make it easy to use, I guess, it's very limited. It only does univariate data and only a very particular transformation of the univariate data. So if you use the file approach, you have much flexibility in your sounds, but I think it's harder to learn. And these existing end-user tools are very limited. So I thought, considering all these issues and also that we don't have a good way of embedding the sound in business intelligence dashboards, I thought it was very important that we have a Shiny widget for making data music in our business intelligence dashboards. And so here's an example. Is it this? Okay, yeah. Yeah, this one is the Johnson & Johnson quarterly earnings represented as the logarithm of the logarithm of the frequency corresponds to the earnings in dollars or something. And because it's shiny, we can drag these sliders to change like the speed. Yeah, or we can subset the data. We can say just use the recent years. And I'm not playing at the moment the fourth quarter, but if we add the fourth quarter in, you'll hear that there's this dip at the fourth quarter. And also, we can switch the melody. We don't have to use the Johnson & Johnson quarterly earnings. We can use the Mario melody. Yeah. Okay. Now this, one of the reasons the way this works in the end, there was that JavaScript code at the bottom. That's the majority of the song, and then it's manipulated with the R code. And this song representation is purposely chosen. It's a standard song representation that's used in many JavaScript packages. So the general strategy for using this is you take an existing song and you add parameters to that song. You go to this website that has a bunch of these songs, and then you copy the song and you you do something like this. This is a very simplified example. Here we have a function. It's the same thing as the speaker that moves back and forth. We get the time in seconds, I think. And here it's going to be a sine wave. So we're going to sine wave with frequency 440. This doesn't have any connection to R. To make it connected to R, and some of the songs will already have this because this is part of the format, but most of them won't. You use this state variable. And so we say that from R we're going to get the value, the frequency, and instead of saying exactly 440, we're going to use whatever the frequency value is. And this function will get evaluated like 50,000 times per second in order to produce the sound. It gets evaluated in the JavaScript and it gets sent through a web audio stream or something like that. And then in the R code, we make the Shiny widget and we give it the JavaScript code, which could be from a Shiny input field or it could be hard-coded. And then everything else gets passed into that JavaScript state variable. So here's the full code for the very simple example I'll show you. Oops. Yeah, so this one is just the sine wave. And when we drag the slider, the frequency changes. And what's happening there is, wait, where was it? Yeah, okay. What's happening there is the frequency comes in through the slider input, and then it goes to the state variable, the frequency, because we set that over here. And yeah, we can change this again. Yeah. Okay. Yeah. So I would like to close with some comments on the practical applications of data music. First of all, for me it's very good because I'm lonely and people like my data music, so I'm hoping that you'll like it and you'll come up and talk to me afterwards. But you all probably have enough friends already. So it might be useful for people who can't see that, that sonify package in R. That was the motivation for that, I think. I haven't done anything this, but this is my next plan to try to make tools for people who can't see, or sound tools. Another thing that's already shown to be very practical is for pretending that data are valuable. The great philosopher Dijkstra said, "We should never forget the crucial distinction between the salesman and the scientist. It is the salesman's duty to please his customers, or if that is too difficult, to fool them." And this is very relevant to data science because most of the time the data aren't actually useful, so we need things like data music to make people think that they are actually very cool. So it's good for convincing your clients that you have a very high-tech product. It's very good for convincing your workers that data science methods are interesting enough to make up for terrible jobs and dismal career prospects. And it's also good for convincing yourself that you yourself are doing something interesting with your life. But the most interesting thing for me is the idea that we might be able to use this for multivariate data analysis. Here's how I think about it. In the past, we had data and we made visuals and we looked at them with our eyes. But now we have big data. See, big data. And so it doesn't fit in our eyes anymore. But maybe if we use music and video, we can represent the big data. And here's an example of this idea written not in Shiny. This has about 20, oh, it's too dark. Oh well. This has about 20 variables in it. And it's the video is about the flights to and from the Budapest airport, and the audio is about various indicators of Hungary and Budapest. 20 variables. I would not be able to fit that in a single visual. But perhaps we can go even further. Maybe we can use all 5 senses. So it turns out the French word for pie chart is camembert, and like we have these things like RStudio, and I was always annoyed we don't have music in the RStudio, so I thought we should make some real camembert. So here's a representation of the top companies in the French stock exchange as cheese. The cooking method and the type of milk and other things represent the cheese, and then the position on this scatter plot represents the dividend yield and the price-earning ratio. So I'm sure many of you will go back to work and you'll implement data music in your Shiny dashboards, but for everyone else, there is still something you can learn about data visualization from this talk. It's good to think of data analysis as a translation of abstract data into our brains. So we should think about how people are going to perceive our data analyses, and if we do that, then we can invent new forms of data analysis that are suited to our particular applications. Thank you. how do I handle if I have multiple variables? Or also, maybe you're not thinking of this, but multiple instruments. Yeah. In the end, the sound is a series of numbers between, well, in this example, -1 and 1, and somehow you have to get it to that. You can read about how, like, if you're playing with like 100 different instruments well, let's say you have a band and you have 4 different instruments. In the end, you can collapse all that sound into one thing. So if you read about like just how sound works and how music works, that'll make sense. And I can show you some examples, but. Yeah. So one idea is if you have 4 lines of data, you might want to listen to each of them separately and maybe combine them and detach them. So a lot of these operations are very simple. For a lot of operations, just like simple multiplication and addition does more than it works much better than you might expect. But the other thing I should note is there are other ways you could represent the sound. Here I said each note is a datum and the frequency corresponds to the earnings. But you could do something else. You could say like the frequency corresponds to something, the speed corresponds to something else, the type of instrument, like you could make it be a string instrument versus a wind instrument, that could correspond to something else. And I have many examples of this on the website. You could see more complex examples. Okay, we're out of time. Thank you.